Okay, it's 2:30. We're going to get started. Just waiting for people to stop talking. Okay, so we're starting today with the same exact Mr. Beast problem we had a few days ago. A few days ago, we said the limit of how much money Mr. Beast gives us goes to 0, right? First he gives us $900, then 90, then 9, and the numbers are getting smaller and smaller, and we did all this visualization. This was the idea of a limit getting closer and closer to 0. That's what we did last time. We learned about what is a limit. Today, we're learning about the total amount of money that Mr. Beast gave us. So that's what we're doing. Let's see what you guys said. What is the total amount? So on day 1, he gave us $9,000. On day 2, he gave us $900, so our total was $9,900. On day 3, 5 people said he's given us $90, but we're looking for the total. So it's not 90. Let's see if more people got it right. Maybe down here. Yeah, all right. 91 people got it right. 9,990. He gave us an extra $90 on day 3, so we're up to 9,990. Are there any questions or comments? Lots of people talking. Okay. I will wait for people to stop talking. Okay, so on day 3, 9,990. On day 4, 9,999. Right? He gives us an extra $9 to pay for the tax on the $90 he gave us the day before. On the next day, what is it? Oh my God, let's see. Is it here somewhere? Lots of different good guesses. So 90 cents is what he gave us on day 5. What is S5? That's the total. 72 people got it right. 9,999.9. That's on the 5th day. So that's the pattern. 9,000, 9,900, 9,909, 9,909.9. Where is this going? Where is this going? What is the final limit? That is, what is it getting closer and closer to? And how many people got it right? $10,000. It's getting close to $10,000, and I guess just around half the people got it right. Some people said it was 1,000, but we started with 9,000, so it's going to be at least 9,000. It's getting closer and closer to 10,000. So let's write down what happened in this question. We did this thing. We did 9,000 plus 900 plus 90 plus 9 plus 0.9, and here I'm going to do plus ... and this means add them up forever. Add them up forever. And what is it getting closer and closer to? It's getting close to the number. We think this infinite sum of infinitely many things, we think this is 10,000. It's getting closer and closer to 10,000. So that's what we're doing in today's class. We're looking at sums like this. These sums are sometimes called series. So we're starting in section 8.5 called series. And this one is an example of an infinite series. This is on page 322. We're doing sums like this. Before we start doing all the hardcore math and like all these crazy symbols and Greek letters and stuff, I want to point out something very simple. Imagine you're in this story and you are Mr. Beast and you're trying to think to yourself, I want to give away $9,000. Instead of doing this whole shebang with $9,000, then 900, then 90, this is like a pain in the ass. Like this is going to take me infinitely many days. Can we do it in one shot? So Mr. Beast thinks to himself, is there an amount of money that I could give in one shot? Right? So instead of giving you a little bit of money every day and then paying for the tax for the day before and then it all adds up, could he do it in one shot? So let's pretend X is the amount of money. Let's say X is the amount. And instead of giving us 9,999 and so on, what if he just gave us X dollars and X covered the $9,000 plus the tax, right? Amount to give us. So if he's going to give us X, we have to pay tax. So we get, what do we get? We get 100% minus 10%, that's the tax, times X, right? This is the tax. And Mr. Beast wants to set it up so the amount we get is $9,000. So let's erase this. We get $9,000. $9,000. So Mr. Beast is trying to solve for number X such that 100% minus 10% of x is $9,000. And Mr. Beast knows how to divide equations just as well as everybody else. Therefore, what is x? Let's move this stuff to the other side. Move 100% minus 10% to the other side. Therefore, x equals 9,000 divided by 90%. Or in other words, 9,000 divided by 0.9. What is 9,000 divided by 0.9? It is $10,000. So of course it perfectly matches what we did before. Mr. Beast has two choices. He can give us $10,000 once and be done with it, and then we'll just have $9,000 after we pay $1,000 in tax. Or he could give us a little bit of money every day for the rest of eternity in this funny pattern. Both of them are the same thing. And that's what we're going to learn sort of today, is that these infinite series, even though it seems like you're adding up infinitely many things, there's a lot of situations where it simplifies, and you can solve it. You can figure out what is the actual number that it should be. Okay. Any questions or comments about that one? I'm hearing a lot of talking. Maybe something was unclear. This is all motivating why we care about series, rather than just jumping in to crazy symbols. Okay, so I guess you guys want to see the crazy symbols then. We're going to start with these crazy symbols. So we're starting with series. And the first thing you got to know for series is, what does this crazy letter over here mean? What does this letter mean? So you got to learn what this letter means and what all these symbols around it mean. I will start by telling you what is the letter sigma. This is the letter sigma. Sigma. And this is a Greek letter. It's an uppercase Greek letter. So if you go to Greece, you'll see this on the walls and things. So really, it would have been better if we had written S. So we could have written S. S, I equals 1 to n. AI, that would be the same thing, writing a big S. But I don't know, whoever decided to do this decided Greek was cooler, so they're doing it in Greek. And it stands for sum. So what this means, if somebody writes this down, they are saying, please add up a bunch of numbers. So if you see this stuff, this means, please add up a bunch of stuff. That's what the big letter means. And then the details are written above and below. So here are the details that you got to keep your eye on. There's the bottom, the top, and last but not least, the thing you are summing. So this thing on the bottom tells you where to start. This is where to start. The thing on the top is where to end. Where to end. Everybody knows start is red and end is green. Where to end. And the thing in orange is what to add up. What to add up. So when you see this funny symbol, you got to read these three parts. Where to start, where to end, and what to add up. Here is the example they gave you. They said if somebody wants you to add up the sequence AI, and they want to start at I equals 1 is the first thing, and I equals n is the last thing, that is this variable 1, 2, 3, 4, all the way up to n. So I goes from 1 to n, and because I is going from 1 to n, we have a1 plus a2 plus a3 all the way up to plus an. So this funny symbol over here means exactly the sum of n things. This letter I is sometimes called a dummy variable. So sometimes people call this I a dummy variable. Let me draw that. I is a dummy variable. Why is it a dummy variable? Because it's not actually a variable, it's just telling you what numbers to sum up. So we want to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to n. How do I specify that? I give it a name. I'm just going to call that I, and please sum up all the I values between 1 and n. So that's the example in the notes. Let me also do it for our Mr. Beast problem. I will write down the same thing over here. Let's add a page. So how would we write down this fact that 9,000 plus 900 plus 90 plus 9 plus 0.9 plus dot 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 equals 1,000 or 10,000? That was a fact we did already. You can write, anytime you have a big sum like that, you can write it in the sum notation. So what I'm going to do is I'm going to write it over here. I'm going to write it as a big sum. And I have to choose what letter I want to do and where do I want to start. I'm going to start at 1. So I equals 1. I'm going to make this the first term. This is the first term. I'm going to call this A1. I'm going to call this one A2. And if you watch the video on geometric sequences, you can figure out a formula for AI. The formula is 9,000 times 0.1 to the power I minus 1. So this formula comes from the geometric sequences video, the formula for a geometric sequence, which was the extra video, sorry, not the extra video, the recorded lecture video. The formula for a geometric sequence, it's 9,000 and it shrinks by 10% every time you add a term. And we're adding it up. We're adding up the dummy variable starting at I equals 1, and we want to do it forever. And when you want to do it forever, you set the endpoint to infinity. The endpoint is infinity, sum forever. So you could just say the sum of all the numbers is 10,000, or you could write this big scary sum with the big Greek sigma and say that this sum equals 10,000. They mean exactly the same thing. This crazy scary big sum just means this sequence of adding things up. Okay, and sometimes the ending point is infinity. That means go forever. So sum over all possible I values. I'll say one more thing. Some people who like programming find this helpful. If you don't like programming, then just ignore this. Some people think of this as a for loop. This is a for loop. This is for I is equal to 1 to infinity. And then you make your sum. You start sum at 0, and then you do sum plus equal AI. So if you like programming, and you know programming already, and you want to understand what the hell this crazy sigma means, there is a little program that is evaluating sigma. If you don't know programming, then don't worry about that. Okay, so what have we done so far? We've learned this funny notation. We've seen one example of an infinite sum. Here are some notes, which are the things I said already out loud. I'll go back to this one. Any questions or comments about this thing? So it's a new notation to write down sums. We're going to learn about these sums. Okay, let's move on to the stuff in the notes. So in the notes, they give you this example, A1 to AN. Here is another example where they tried to change up the variables. And in this one, they are using R instead of I, which is totally fine. You can use any letter you want. It will represent the same thing. So for example, you could write this is equal to the sum from I equals 2 to 5 of UI. That would be the same exact thing. You can change the letter of a dummy variable however you want. Okay. And what does it mean? In this case, we're starting at 2 and we're ending at 5, so it means please sum them up from 2 to 5. So it's the sum of U2, U3, U4, and U5. Exercise 146 is the first example with numbers. Let's do this one. The sum from I equals 1 to 3 of 2 to the power I. So we're going to start at I equals 1. There's going to be one term for I equals 1. There's going to be one term for I equals 2. And there's going to be one term for I equals 3. And we're going to add them up. So plus signs between everybody. And we just plug in 1, 2, and 3 to get the three numbers that we're talking about. The first number, 2 to the power 1. The second number is 2 to the power 2, right? I equals 2. And the third number is 2 to the power 3. So you could just leave it like that, 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3. You could also figure out what they are. That's 2 plus 4 plus 8, also known as 14. So there you go. Exercise 146, adding up three numbers in the notation. The answer was 14. We're about to do an infinite one. I sort of teased an infinite one already. Any questions about the notation or anything, how it works so far? No, okay. Here is the same idea, where if the endpoint is infinity, like I said before, you add up forever. So you say plus dot dot dot, you add them up forever. And I've tried to show you guys already in this course that even though adding up infinitely many things seems like it should always be infinity, sometimes it's not. Sometimes it's a number like 10,000. And the example that they give you is this example. This is a picture proof. This is a picture proof. Exercise 147 is a picture proof of what? Of the fact that you can take something of length 1 and you can write it as an infinite sum of things that are half the size of the other thing. So the whole interval of length 1, you can go halfway between there and there. That's a half. And then you can add on a quarter. That's from here to here. Then you can add on an eighth. That's from here to here. And then you add on 1/16. That's from here to here. And then you add on 1/32. That's from here to here. 1 over 32. No, 1 over 16 is next. Okay, I lied. But you keep on adding half of whatever is left. And if you do this, you're adding up infinitely many things. This is exactly what that Greek philosopher Zeno was thinking about Before you go all the way from 1 to 0, you have to go halfway. Before you go halfway, you have to go a quarter of the way. You have to do infinitely many things to get from 0 to 1, but the sum is 1. So this is a picture proof. This is a picture proof of this fact that 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... That is doing all the intervals there. A half plus a quarter plus an eighth are these intervals. And if you add them up, you get the full interval, which is length 1. So 1/2 plus a quarter plus an eighth plus a 16th plus ... equals 1. You could write it like that. You could also write it with the sum notation we had before. How would you write it with the sum notation that we had before? You would convert this thing to a formula, and the formula is 1 over 2 to the power I. So the ith term, I is just some dummy variable, is 1 over 2 to the power I. So when I equals 1, you get a half. When I equals 2, you get a quarter. That's the second term. The formula is 1 over 2 to the power I, so you would write this entire sum like this. The sum from I equals 1 to infinity of 1 over 2 to the power I is equal to 1. So here is it, the same fact 3 times, written once like that with a ... written once like this with a sum notation, and written once as a picture proof, as a picture. All 3 things are the same thing. Okay. Any questions about any of those? So it should be surprising that you can do infinitely many things and still get only 1, right? This was like those flipping the cups. If it takes you half as long to flip the next cup as the first cup, you can flip infinitely many cups in 1 minute. That's okay. All right, any questions or comments about this one? I will say, you could also do this one the same way as the Mr. Beast thing. You could say, Mr. Beast wants to give us $1. Mr. Beast wants to give us $1, and the tax rate is 50%. So if Mr. Beast wants to give us $1 and the tax rate is 50%, you can work out what's going to happen, and you're going to get the exact same kind of thing, that he should just give us, I guess he wants to give us $0.50. He wants to give us whatever the first term is. So let me fix this. Mr. Beast wants to give us $0.50. So this is like the poor version of Mr. Beast, who is broke, and instead of giving out thousands of dollars, only gives out $0.50. So if he wants to give out $0.50 and the tax rate is 50%, how much money should he give us so that his whole infinite sequence of paying for the tax works out? If he just gives us $1 to start with, then we'll get $0.50 after our tax rate. So you can work it out also logically with this idea. Okay, that is an infinite sum. Any questions or comments about that? I'm gonna take a break and take a little drink of water while you guys think of questions. Okay, no questions. So the Greek philosophers took hundreds of years to absorb this, and they got grumpy and killed each other over this fact that adding up infinitely many things can happen, but you guys are okay with it. Okay, good. Here are some more. Let's do the sum of 3 over 10 to the power I. Let's do this sum. And we're going to do it by writing it out. So we're not going to do it in some funny algebra way. We're just going to understand what the sum is, and we're going to do it, quote, on our calculator. So I'm just going to write out what the terms are. 3 over 10 to the I, that means we're starting at I equals 1, and we want to go forever. So I'm going to calculate all the terms. When I equals 1, you get something. When I equals 2, you get something else. When I equals 3, you get something else. And I want you to add them all up. And because I'm ending at infinity, you just do plus ... That means go forever. So let's write out the first few terms and see what we get. The first term is 3 over 10 to the power 1. 3 over 10 to the power 1. The next term is 3 over 10 to the power 2. The next term is 3 over 10 to the power 3. Okay, you can keep going. It goes on forever. That's why we do plus ... That means it goes on forever. Now we can simplify these by converting them to decimals. What is 3 over 10 to the power 1? That's 3/10, 0.3. Okay. What about the next term? 3/100 is 0.03. 3/1000, 0.003, right? Every time you divide by 10, you move the decimal place over 1. And we're going to do this plus ... So what's the pattern? 0.3 plus 0.03 plus 0.003 You get the number 0.3, then the next 3 comes, then the next 3 comes, then the next 3 comes, dot, dot, dot. The 3's repeat forever. You get 0.333 repeating, of course. What is 0.333 repeating, of course? You've probably seen it on your calculator before. This is also known as the fraction 1/3. 1/3. So the answer is 1/3 just by kind of calculator math. We're going to learn later on, we're going to learn a proper way to sort of do this and make sure we know how the answer is 1/3 without sort of writing down all the terms. Just by combining the numbers 3 and 10, you can combine them in the right way to get 1/3 just by algebra without having to do this intermediate stuff. Questions or comments about that example? 0.333 repeating. I think a lot of people are okay with 0.333 repeating as 1/3, but they're not okay with 0.99 repeating as 1. One statement is just 3 times the other statement. So it is interesting that this one people are okay with. Okay, let's do another one. See if you can guess what this one is. I'm going to write out the first few terms, see if you can guess the answer. So we got I equals 1 to infinity. Got to do it one more time. I equals 1, add it to I equals 2, add it to I equals 3, and so on. When I equals 1, you get 2 to the power 1. When I equals 2, you get 2 to the power 2. When I equals 3, you get 2 to the power 3. And we are doing plus dot 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 because we are going go forever. Go forever. Okay, so this is the sequence. 2 plus 4 plus 8 plus 16 plus dot dot dot. It goes on forever. What do you get when you add these up? 2 plus 4 makes 6, plus 8 is 14, plus 16, 31. Did I screw up my math somewhere? 30. It's 30. Okay. The numbers get bigger and bigger. You're adding on bigger and bigger numbers. What happens when you add up infinitely many big numbers? You're, of course, going to get infinity. It's infinity. You could say because adding up numbers getting bigger and bigger. Numbers. Let's say the numbers get bigger and bigger. The numbers get bigger and bigger. And they just get bigger and bigger forever. Before, the numbers were getting really small, and that is why you could add up infinitely many numbers, and it would be something. This would be like trying to flip a cup, where every time you flip a cup, the next cup takes you twice as long. Then it's going to take you infinitely many years to flip the cups. So the answer is equals infinity. That's what's written in the notes. I will tell you, this upsets me a little bit, because this equal sign over here, equals is something that should go between numbers, right? This number equals that number. And to me, this is not an equal sign. So I don't know, put this in quotes or something. This is equal. How could it be equal? Because infinity, not a number. Not a number. So I would watch out for that. That equal sign is a treacherous equal sign. And really what's going on is there is a certain limit, and we talked about what does it mean for the limit to be infinity. This is some kind of limit. This is some kind of limit. So there is some kind of limit hiding underneath everything here. And that limit is infinity. I wouldn't say that it's equal to a number. This thing on the left is not a number because, it's not a number. So it's kind of slippery to understand. To make sense of this, we actually have to understand that these infinite sums are actually limits. That's what's going to happen on the next page. The limit of a series. So this is a good place. This kind of like motivates why we have to understand this with limits. Otherwise, we run into these not a number situations. Okay. Any questions or comments so far about these sums and what's going on? So these sums are actually, doing an infinite sum is actually just doing a limit. So here is the definition 64, the limit of a series. So this word series just means a sum. Series means sum. I don't know who invented a new word for the word sum. We already have a word for it, but okay, it's series. The limit of a series is the value that the series approaches as the number of terms becomes large. So just like before, we're doing a limit. We're doing the limit not of the individual terms, not of the $9.90, 9 cents that Mr. Beast gives us, but the total amount of money. That's the limit of the series. If the limit is infinite, then the series is called divergent. In general, if the limit does not exist, it's also called divergent. If the limit does not exist, it's also divergent. Does not exist. It's also divergent. Okay? So in all these situations, this like magical phrase, DNE, right? DNE, like that, means the limit does not exist. And when the limit does not exist, we call it divergent. If the limit does exist, and it's some number, then we call it convergent. So it's just like limits before. The words divergent and convergent means either the limit exists or not. Okay. Sometimes people call them summable. So if the limit of the sum exists, it's called summable. Okay, here's the same definition, but written with math. So you have the sequence S. Capital S is the sequence of sums. So S is the A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3, then there's a comma, and then S4 is A1 plus A2 plus A3 plus A4, and that goes on forever, right? So S, some subscript, tells you how many terms to add up. If the limit of Sn exists, you look at the limit of Sn, if that exists and is equal to S, then the infinite series is convergent. So convergent means the limit exists. And in that situation, you could write the sum from 1 to infinity of AI is equal to S. So whatever S is, whatever the limit of that thing is, that's the infinite sum. Infinite sums are actually limits. They're the limits of the partial sums, S1, S2, S3. Okay, if no limit exists, then it's called divergent. So these are the same definition twice, once with symbols and once in just words. And it's kind of a subtle idea that you can add up infinitely many things and have some non-zero thing. It's all packaged into the idea of a limit we saw 2 classes ago about getting really, really close to. Okay, any questions, comments? Okay, here's one. Here's one to do. This is the same one we did already. The limit from I equals 1 to infinity of 1 over 2 to the I, example 147, is what we did already. The sequence here is AI is 1 over 2 to the power I, right? So what is S1? It's just A1, the sum of just the first term. Here I equals 1, it's 1 over 2. What is S2? It's A1 plus A2. It's 1 half, 1 over 2 to the power 1, plus 1 over 2 to the power 2, which is a half plus a quarter. A half plus a quarter. And a half plus a quarter is the same thing as 3/4. Everybody who likes to bake stuff knows that. Okay, 3/4 of a cup. Okay. What about S3? So S3, you could write it all out again. It's 1 over 2 to the 1 plus 1 over 2 squared plus 1 over 2 cubed. But an easier way to do it, I think, is to just use the fact that we're just tacking on A3. We're tacking that on to S2. So actually, this is 3/4 plus 1/8. Right? We take whatever we had before, A1 plus A2, and we're adding on the next term, 1/8. Before it was 3/4, now we're adding on 1/8. What is 3/4 plus 1/8? So if you do the fractions, 3/4 is 6/8, and we're adding on one more eighth, that's 7/8. So the pattern 1 half, 3/4, 7/8. The next one is going to be 7/8 plus the next term, right? All of the first 3 terms together, they make 7/8. And then we're adding on the next term. The next term is 1/16. A4 is 1/16. What is 7/8 plus 1/16? Again, you can make 7/8 into 14/16. The answer is 15/16. Okay, so what's the sequence? The whole sequence together, S1, S2, S3, S4, is the sequence 1 half, 3/4, 7/8, 15/16, ... If you have a keen eye, you will see the pattern. The bottom, the denominator, is always powers of 2, 2, 4, 8, 16. The numerator is always 1 less than the same power of 2. The numerator is always 1 less than the denominator. So the denominator for the nth term is 2 to the power n. The numerator is just 1 less. It's 2 to the n minus 1. This is the pattern. So if you wanted, you could write them like that. You could write the formula. And I just did that by sort of guess and check. We're going to see later on, and in fact, we've already seen how you get the sum formula. That was in one of the videos as well. But that is the pattern here. And here is the thing about the limit 2 to the n minus 1 over 2 to the n. And I think the limit is written on the next page. Yeah, it's maybe 2 pages down. This is telling me to do what I just did. We're going to go to this page. Here is the answer we just had. The series has these partial sums, 1/2, 3/4, 7/8, and so on. The nth term is the formula I just said, is 2 to the n minus 1 over 2 to the n, which is the same thing as 1 minus 1 over 2 to the n. Or you could write it like this, 1 minus 1/2, let's make it look really suggestive, let's make it 0.5 to the power n. That's the formula. So what is the limit? The limit as n goes to infinity is 1 minus 0.5 to the power n, 0.5 to the power n. That's what we're at. We're trying to calculate the limit. What does it get to as the numbers get bigger and bigger? It's that limit. We did a limit just like this last class. In fact, it might have been literally this one. Oh, I think it was 1 minus 1 over n. This is exactly the kind of limit you can split up into two parts. There's the part at the front, the 1. There's the part at the back, the 0.5 to the power n. So what is the limit? Well, the limit of just 1, is 1. So the first term is 1. What is the limit of 0.5 to the n? This was a rule. We said the limit of 0.5 to the n is going to be 0. The limit as n goes to infinity of 0.5 to the n equals 0 by the rule. What was it? The geometric series with geometric rule? So we had this thing, we had b to the power n, and depending on what b is, the limit was either 0 or infinity or 1. In this case, the limit is 0. So the limit is 1 minus 0. The limit of the first term, the 1, is just 1. The limit of the second term, 0.5 to the n, is just 0. What is the limit of everything together? It's 1 minus 0. 1 minus 0, also known as everybody's favorite number, 1. So we've proven, or we've shown, that the limit of the sequence Sn is 1, and the limit of Sn is 1. That is the same exact statement as saying that the infinite sum of 1 over 2 to the I equals 1. So when someone says an infinite sum, they mean the limit of the Sn's. And the limit of the Sn's was 1, so our sum is 1. Okay. I think the very next thing is that you guys are going to do one on your own. So this is a good place to stop for any questions or comments of doing these infinite sums. Okay, so I'm going to set you loose on this next problem. Exercise 152 in Math1030. Try to do it. It's the same kind of thing as before. Figure out what is S1, S2, S3, S4. Look at that sequence and then do the limit of that sequence. That limit will tell you what this infinite sum means. Okay, I'm going to open it up in Math1030 and give you a couple minutes to try it out. And by the way, the code, in case you missed the code is ZTAX. ZTAX. I only have like 70 answers. Who needs a little bit more time? Okay, let me give you guys another minute or so here to try this one out. Guess, if you're not sure, like 10 seconds now. Do as much as you can, put in a guess for the limit. At what you guys think the limits are. So first of all, what are the terms? If you can't figure out the terms, you have no hope to do the limit. 131 people think it's -1. It is -1. That's right. Very good. All right. What is the next one? Let's see if 131 people got the next one right. 0 is popular. 1, only 15 people chose 1. That's excellent because the answer is 0. So good work, everybody. Let's see how this works. The first term is -1. Oh, they were written here. Okay, I didn't realize. Maybe you were just... -1 plus 1 is 0. To go from S1 to S2, you add on the next term. You add on 1, and then you get 0. Very good. What about to go from S2 to S3? What do you get there? S2 to S3, you get... Oh, where is it? Oh, my goodness. Ah, -1. There it is. Okay, good job, guys. So the next term, 0, you tack on a -1. 0 plus -1, also known as -1. Is there a comment? Questions? So far it's -1, 0, -1. The next term, you add on 1, is going to be 0. So all the first three terms together are -1. Then you do -1. The last term is 1. You get 0. -1, 0, -1, 0. So the sequence is this. -1, 0, -1, 0, ... Now you need to know what is the limit of this sequence. What is the limit? The limit is, oh my goodness, lots of, oh, okay, wait, hold on. This is A1 to A4. Okay, this one was 0. Okay, good, 0. What is the limit? What do people think the limit is? 34 people think the limit is 0. 20 people think the limit is 1. 32 people think it's -1. 40 people think it does not exist. 40 is the biggest number, and that is the correct answer. So the plurality of people, 28% of people got it right. How do you enter in does not exist? You type in the letters D-N-E. D-N-E. D-N-E does not exist. This limit does not exist. It's not 0 or 1 or -1. And the reason it's not any of these things is because it never settles down. A limit is the idea of getting really, really close to something. I'll pause and wait for people to... I know it's very exciting when the limit doesn't exist, guys. So the limit doesn't exist because it never settles down. It's jumping between -1 and 0, -1, 0, -1, 0, and it never settles down. Because it never settles down, it's alternating between -1 and 0. Thus, the sequence, I'll say the limit does not exist. Thus, the limit of Sn does not exist. The limit of the Sns does not exist. The limit of the sums doesn't exist. So the sequence of -1 to the n is not summable, I'm going to say. Not summable. Not summable. So the sequence is the sequence -1 to the I. The limit of the sums doesn't exist. The sequence itself is not summable. And the series, we would say, is divergent. Oh, that's a good word. Divergent. Okay. There you go. That's one where the limit doesn't exist. Of course, the limit cannot exist in all sorts of ways. That's just one of them, where it's bouncing around and never settles down. Another way the limit might not exist is it might go up to infinity. I believe that's the next example. No, it is not. So another possible one here. I'll give one more example near the bottom here. If you do the sum from I equals 1 to infinity of 2 to the I, this is also divergent. Also divergent. So the limit won't exist. We did this one before. This is 2 plus 4 plus 6, 2 plus 4 plus 8 plus 16, and so on. It's divergent, but this one is infinity. So you could write it equals infinity because it's divergent, but it's the type of divergent that is going arbitrarily large. So the limit is infinity. So both of these are two examples where it doesn't exist. The limit is not existing, but in two different ways. Okay. So what have we done so far? We've learned about this funny sum notation. I've shown you guys one application in real life, the Mr. Beast example of where we care about it. In the next section, we're going to learn some tricks for actually evaluating these sums. That's the next section here. This one is a self-study. This is totally optional. This is optional. Optional. Feel free to skip this one. I'm talking about this section. So this is algebra of series, and this is telling you how do you manipulate the series to try to find their answer. How do you manipulate them to find the answer? And I'm going to skip all the way down. I'm going to skip all the way down to here, to result 35. Don't worry about the other stuff. Result 35 tells you how to do sums. It tells you if you have a sum like this, the answer is that. The sum of something is something else. Here is the example they gave. The example they gave is the sum from I equals 1 to 3 of 5. I equals 1 to 3 of 5. This means I is going from 1 to 3. I is 1. Then I is 2. Then I is 3. And what are we adding up? It's the sequence that's always 5. So it's 5 plus 5 plus 5. What is 5 plus 5 plus 5? 5 plus 5 is 10, plus one more 5 is 15. So you can add it up and get 5. Or, look at this savings, guys. You could use this formula. In our situation, k is the thing that we're summing up. That's always 5. And n is the number of terms. In this case, that's 3. So the formula says you can skip all this hard work of 5 plus 5 plus 5, and you can just do 3 times 5. 3 times 5 is 15. So that's all this formula says. Instead of adding up the same number over and over again, you can multiply. Great. Okay, very good. It seems kind of silly when you're doing a sum like this, but if you have a sum with a billion things in it, what is the sum from I equals 1 to 3 billion of 5? This one is easy in one way and hard in the other way. Okay. That's trick number 1, result 35. There are some more tricks. Here's some more tricks. One is you can do a common multiple, so you can take a factor of k and pull it out. If you have a factor of k, you can pull it out. If you want to split up a sequence into two parts, you can add them up separately. All of these reflect the rules of sums that you can add in any order you want. Okay, and here are the examples they went with. Let's see. Let's make this one an extra one. I'm going to make this one extra. I'll post it online. But this one we'll do. We'll do this one. And there's a space for it over here. So this one will be extra. But let's do this one right now. Let's do this one right now. This is how would you do this sum? It's an infinite sum, and it has this funny thing, 1 over 2 to the I plus 3. You could try to figure out what it is. When I equals 1, the first term is 1 over 16, and then the next term is 1 over 32. But we're going to do it with algebra. And how are we going to do it with algebra? I'm going to simplify. 1 over 2 to the I plus 3 is the same thing as 1 over 2 to the I times 2 to the 3. So adding in the exponent is multiplying outside the exponent. I should not forget to write this whole big sum. And now, one of the rules says that if you have a term, you have a constant multiple, like this 8 over here. This 2 cubed is a constant multiple. It's in every single term. You can pull a constant multiple out of the sum. So this is equal to 1 over 2 cubed times the sum from I equals 1 to infinity of 1 over 2 to the I. So I can take out that factor of 1/8, 1 over 2 cubed. I can pull that out of the whole sum. That's exactly 1/8, 1 over 8. Okay. What is this crazy sum over here? We just did this. This is the sum of a half plus a quarter plus an eighth. That was the thing we worked really hard to show was equal to 1. So this is 1/8 times 1. So what is the whole thing? It's 1/8. So that is one way you can do these big sums. Okay, the other one is quite simple. I'll post an extra video of that. Let me give you a preview of what is coming up. What is coming up is some special series. It's the sum of an arithmetic sequence, which is this weirdo-looking formula. And then there's also the sum of a geometric sequence. Both of these we already did in those videos from the Friday before reading week. So if you haven't seen those videos, really watch them, because next class I'm going to say, we're going to skip a lot of this work. We're only going to do a little piece of it because we already did it in the video. So make sure you watch it before then. Otherwise, have a good weekend, and I'll see you guys on Monday.